Okay, I wanted to continue with Monte Carlo. I introduced the very basics of Monte Carlo simulations, but until now it's not very realistic. And step by step, I think we slightly approach a more realistic description of alloys using Monte Carlo simulations. In particular, that's important for kinetic Monte Carlo, where you try to follow the time evolution typically towards equilibrium, but not necessarily. At the very end, probably I will give a short overview about what I did a long time ago on irradiation effects. There you are not in equilibrium, you are not approaching equilibrium, but still you are approaching stationary states if you are lucky enough. Yeah? That's something slightly different. And there are a couple of things missing. So first, if we are discussing time evolution in alloys, we have to consider vacancies instead of these AB exchanges. This is true in most cases. Of course, I showed that there is also interstitial diffusion, but typically we consider substitutional elements and substitutional diffusion via vacancies. So that's the first point. Then, and that's closely connected to this point, there is one might call it complication or refinement, a complication that often in vacancy diffusion you will have very high activation energies to overcome this barrier. And this means that many of the attempts made, I mean, we make this jump only with a exponentially decaying probability. If the activation energy is too high, then these successful attempts become very few and the unsuccessful attempts become many. Yeah? So this means you waste a lot of time. And the way out of it is a so-called residence algorithm, about which Guru will speak afterwards. So very simple said, instead of making all these unsuccessful attempts, you calculate how much time the system would spend in this state which it cannot leave for a long time. And then you do the next jump for sure. So you don't waste this time, but instead you calculate the wasted time. Yeah? That's the basic idea of this algorithm. And this also, besides this gain in computer time, it also allows to give more realistic timescales to the time evolution. Normally in Monte Carlo, you count time just in number of Monte Carlo steps or so. I think in the very beginning, Guru introduced it, and still you find this on some of my slides because I was too lazy to get out this time. But typically when I did these Monte Carlo simulations, I always applied this residence time algorithm. Residence time, sorry. And then finally, this will be talks this afternoon, and I already mentioned it, these very simple pair potentials or pair exchange energies, they are not describing a realistic system. And again, I will explain how to go beyond this. So that's the program for today, I think. Okay, one point is missing. Besides this, or it's a bit on the side. Besides this, I will also explain how to calculate phase diagrams inside a Monte Carlo simulation. That's very important, because if you study, for example, a precipitation process or an ordering process as well, you have to know where, for the choice of potential parameters, you are in the phase diagram. This phase diagram is not necessarily a realistic phase diagram. This depends a bit on the choice of potential. But to be consistent, you have to know which concentration corresponds to which supersaturation or so. So I want to start with this first thing, and there is one point. I think it's not often discussed in literature, which comes aside with this vacancy diffusion. So you have your lattice, and one of the lattice sides is unoccupied, and you have your atoms around it, say A and B atoms. Perhaps like this. And then an atom can jump into the vacancy, or the vacancy can jump to a neighboring atom. After a while, if you are used to deal with vacancies, you treat vacancies as particles. But of course, it's just a missing particle, like you do in electronics. You speak of holes, but it's just an unoccupied electronic state. So vacancies are important. But then we have to be a bit careful about the interaction. In principle, one could also introduce interaction energies between the neighboring atoms and the vacancy. Typically, we don't do it. We just assume that the interaction is lost here, broken bond model. But now if you calculate the change in energy if one neighboring atom jumps in there, I will write down the energies here. I mean, basically it's that over 2. I did not go through all these steps here. Plus this parameter epsilon times NAB. And A and B is a total number of A and B atoms. And NAB, capital NAB, is the number of AB bonds. Epsilon AA is the interaction energy of an AA pair and so on. Huh? And this epsilon is this difference in pair exchange energy. And now if we consider an A atom jumping in here, we can calculate that this initial energy now becomes constant that's basically this first term here, plus the number of B neighbors of this side 1 here, times epsilon AB, so A atom jumps plus this is similar to what I explained yesterday. NB of I is the number of B neighbors of B neighbors of this side I. Then you see if this is an A atom here, it takes the number of B neighbors times this energy of AB minus plus Z minus NB. See, this is the number of A neighbors here, epsilon AA, if it is an A atom. And the final energy, after I did the jump, the same constant, now NB, the vacancy is sitting on side 2. So the vacancy is here. So that's the difference. If we subtract these two, NB2 minus NB1, epsilon AB plus, so that cancels out. NB1 minus NB2. Or if you prefer, we can put a minus sign and then have the minus here. So this is like this. And I can make it a bit more complicated. I keep this first term here. But here I wanted to introduce this pair exchange energy. And now I'm missing something. I have here epsilon AB, that's fine. I have 1/2 epsilon AA. So I have to have another 1/2 epsilon AA. And I have to get rid of this epsilon BB here. So it's minus epsilon BB. This is what we already encountered a couple of times. Or epsilon. But this is a term which until now did not appear. And this is the one I wanted to discuss a bit. It's not a common term, but I wanted to call this the asymmetry energy. And if you do the same calculation for a B atom which jumps, you find for this delta E here I have minus this epsilon AS, and now I have a plus epsilon AS. Perhaps I should write, would I? And from these equations, you already see that's why I call it asymmetry energy. In one case, it adds to the epsilon. In the other case, it's subtracted from the epsilon. Yeah? And this means that jumps of A atoms or of B atoms can become easier, whatever sign I choose for this asymmetry energy. So this controls the relative probability that either a B or an A jumps. And this means, in more experimentalist terms, yeah, it's the mobility of the A or the B atoms or the relative diffusion coefficients. And you probably know that diffusion coefficients in a binary alloy of two species, they are not necessarily the same. Yeah? Often you have huge differences in mobility between two species, which can lead to strange effects sometimes. This I wanted to show here.
This is also the microscopic origin of the thermodynamic factor. 1 plus ln gamma by ln x.
Yeah, I know, but I'm not sure.
This is related to how it is changing.
Yeah.
What they say is activity should be related to the.
But I think it's also, I mean, the thermodynamic factor, no, I don't think so. The thermodynamic factor is only important for concentrated alloys. Here it's also for very dilute alloys. Yeah, so I think the thermodynamic factor describes more or less that there is chemical interaction, not only the ideal solution system. Yeah. So here you see couple of simulations, and you see here I marked the time just in Monte Carlo steps. So I did 10 to 7 Monte Carlo steps for different values of this asymmetry parameter. Well, I chose it always positive, but if you do it negative, it would also be important. Yeah. So here the pink curve is for equal probability for alpha R and A and B atoms, and you see here the curves more or less coincide, but the time scale is stretched, yeah, because I forgot what I choose here, probably 10% of B atoms or so. And yeah, the energy, so the axis label here is wrong. That's the energy, the total energy, which I plotted here. But here you see a drastic difference. And that's obvious. Yeah? Here that's the ratio of number of A jumps over the ratio of B jumps. Not the ratio, over the number of B jumps. Here this is for 0. So the ratio becomes pretty large because there are much more. I think I chose 10% of B atoms here. So there are much more A atoms than we have B atoms. So the ratio, yeah, it's not 10, but it's 40 or so. And now if you increase the parameter, you can pull it down here until a very, I don't know whether you see the blue curve here. Here they nearly have equal probability to jump. So, and these are small variations. Yeah? That's 30 millielectron volt, 50 millielectron volts. No huge factors. So I think this parameter is quite important. And that's where this axis labels came from in the other curve. Here's a precipitation experiment on using this Monte Carlo, where I determined the cluster size distribution. I think tomorrow or after tomorrow, Guru will explain how to obtain such a cluster size distribution. It's a tricky algorithm which is applied there. And I'm not sure whether you're familiar. I mean, normally you put a histogram if you want to visualize such a size distribution. So how many particles falling into a certain size class. That's not the best choice I found for Monte Carlo, because typically what I did was a system with 100 by 100 by 100 atoms. So you find total number of clusters, I don't know, several hundred perhaps. So each class, if you make the classes too wide, you don't see the variation. If you make the classes too small, you get a strong scatter. And it's quite difficult to find a good compromise. So I used to typically plot the cumulative size distribution. It's nothing but the integral over this histogram. Yeah? But you avoid to have these histograms. You just count the number of atoms sitting in clusters, say with a size smaller or equal to 200. Yeah? So 1,000 atoms, 1,000 of the B atoms are found in clusters of a size below 200. Yeah? After a while you get used to this presentation. The slope, I mean, if you would take a derivative, this would give you the size distribution as you know it. Yeah? It's just a technical trick, but it avoids certain complications. And because the variation here was pretty large, I used a logarithmic scale here. And you see again that this cluster size distribution is quite different, because of course if you have higher mobility of the B atoms, then you get faster clustering. Yeah? And no, it's not the case here. Look here. So at equal sizes you have less here if you have a positive epsilon. So I don't know, but you see at least there's a considerable difference. And then that's what I try to use it for, you can try to adapt this parameter to real systems in quotation marks. I mean, still we are far away from a real system, but to get some more or less realistic numbers. And that's where I used the diffusion coefficient. So how can we determine a diffusion coefficient from a Monte Carlo simulation? The diffusion coefficient of A or B is given via the Einstein relation by the jump rate of A and B times 1/6 of the jump distance squared. By the way, this factor 1/6, I don't know whether you're familiar with it, it's twice the dimensionality of the system. So in a three-dimensional system, it's 6, in a two-dimensional, it's 4, in a one-dimensional, it's 2. It has nothing to do with the number of next neighbors. So in FCC lattice, where you have 12 neighbors, you still have this factor of 6. Yeah? One can go through this calculation and you find it. So the ratio of diffusion coefficients, since this jump distance is the same, just the ratio of the jump rates. So that's the first thing we need. And then what we do, I think we had it in one of the first lectures already, or someone was asking for it. We take the mean square displacement. That's for a random walk. An atom can jump in different directions. And then you, I mean, in average, that's always a bit difficult for beginners. In average, the atom stays where it started. Yeah? The mean position stays at the starting position because probability to jump back and forth is always the same. Yeah? But this distribution widens like a Gaussian. Yeah? That's why we have to take this x square. Just the square of the distance of the atom. Yeah, here you take this statistical average just by tracing the time. And for this simple relation, and same for B. So if you track, and you can do it for all the A atoms and for all the B atoms in your system, you track the position, and for each jump you add a little bit to this square displacement. And then you get, in most cases, nice straight lines. Here you see this for the A atoms. this mean square displacement is a function of time, and here for the B atoms. For this asymmetry 0, here it's for an asymmetry 33 millielectron volts, and here for a larger value of this asymmetry. You also see that this mean square displacement becomes smaller and smaller here with increasing per exchange, per asymmetry energy. And using this, now you can try to fit this what you know from experiment. I try to use it for system copper-cobalt, standard alloy kind of fruit fly for precipitation experiments, and try to adapt it to this one here. Nickel aluminum is also such a standard case. So that's one how one can try to get more realistic values for this case here by taking experimental values for this ratio of diffusion coefficients, which are equal to the ratio of jump rates, and these you get from these mean square displacements. I don't know whether I have numbers here. No, I have just some view graphs here, some little movies, which now show the formation of these clusters. Here you flickering the growth of these clusters here. This is for 0 electron volts here. The simulation was done for 1 million atoms, 1,000 Monte Carlo steps. So this means overall 1 billion of vacancy jumps. Now you see it here for this 0.33. You see here clusters stay a bit. Here you perhaps see that the growth proceeds to larger sizes here, and here for this 0.05 clusters stay smaller as before. Okay, so this was the point I wanted to make about diffusion and so on, and a small step towards a realistic description. Take diffusion coefficients from experiment and then fit it to these jump rates. Next point is the phase diagrams. So if we are studying a precipitation process, typically we have a visibility gap. Here we have an alpha phase, and somewhere we have a beta phase. And here we have a two-phase field. So that's the concentration of B, and that's the temperature. Something like this. And if you are interested in unmixing, you start here in a supersaturated solid solution, which nominally is in the two-phase region, and then it starts to unmix into these two concentrations here. Like this. I hope this is known to all of you. But now is a question, how can I determine such a phase diagram? I have my interaction parameters. This epsilon, well, basically it's the epsilon. And of course I could do this canonical Monte Carlo simulation starting here and checking which concentration forms here and here. Does it unmix or does it stay here? I mean, if I start here, it stays homogeneous. If I take a higher temperature, it is still homogeneous here, and so on. But this is quite time-consuming and tedious. Yeah? And there is a much easier way. This is kind of transformation of aegis. What do we know about the chemical potential? In particular, in a two-phase region. Do you know? Perhaps you remember equilibrium is given if the chemical potentials are equal. So we have the equilibrium between this composition and this composition if the chemical potential, say, of the B atoms equals the chemical potential of the B atoms in the beta phase. And basically this is because it gives you no energy if you put a B atom from the alpha phase into the beta phase or vice versa. Then they are in equilibrium. So in other words, this means that in the whole two-phase region, the chemical potential is constant. So somewhere out here, perhaps have something like this. And then we have a region of constant chemical potential. And then it goes like this, perhaps. So that's the alpha phase. That's the beta phase. And now we try to revert this curve. So instead of giving the concentration and looking which chemical potential do we have, we give the chemical potential and let the concentration adapt to it. This curve then perhaps looks like this. Just a 90-degree rotation and inversion. Yeah? So you give a chemical potential to the system, slightly increases, and then suddenly it jumps to another value. I'll explain in a moment how we put a chemical potential into this Monte Carlo simulation. There's one small complication. That's why I put these arrows here. You can start from 0 B concentration or from a small B concentration and then slightly increase the chemical potential of the B atoms. Yeah? Then you follow this line here, it jumps here, or you can start from the other side. Then you get a curve like this, and it jumps a bit later. Oops. So you have a certain metastability And if you are lazy and don't want to spend too much time, you just take the middle here. Yeah. Or you try to run it longer. There are other tricks, yeah, a couple of tricks. So how do we incorporate this into the Monte Carlo, into the simple Monte Carlo?
Why is this hysteresis?
Because, I mean, here you start in the beta phase and go into the alpha phase and vice versa. So the beta phase is just metastable here. In principle, one could use these tricks to put the nucleus of the other phase there. I can.
Yeah, so this is associated with the nucleation of the second phase.
Yes, no, yeah.
Yeah, because
I'm not sure. I can check. Perhaps I have my. But I think we tried it. This simple 2D program, yeah. Where do I have it?
Code that did have one GCMC.
Yeah. But I think it did not run, or.
No, I had to compile, but with compilation it did run. With some warnings, but it did run.
Okay. I don't remember. No, it's stupid. There's a MC3. I mean, I did not say this, but of course, this calculation here is for a given temperature. Yeah? So you do this here for a given temperature, or this one here for a given temperature, and then you have to do it for other temperatures as well. Yeah? So if I put a chemical potential of 0, I get 50%. And now I slowly favor the It's very slow. You see here the concentration is 0.47, so I have to use larger values. Now we are here at a concentration of 0.319. Here 0.25. And now I can go to a positive value, then the blue atoms should dominate. Here we are at 55%. But I think this temperature probably is a bit too high. So you should also get these ordered structures here on this triangular lattice. So how do we implement it in Monte Carlo? Very similar to what we had before. The total energy in this grand canonical, it's not really grand canonical, semi-grand canonic. We keep the total number of atoms constant, but allow an A atom to become a B atom and a B atom to become an A atom. So perhaps I should say a few more words. In Monte Carlo, you allow, instead of AB exchange, A becoming a B, B becoming an A. So it's the old sevens making gold from iron. Yeah? Here in Monte Carlo we can. So you can change the composition of your alloy according to a simple rule, and the simple rule is that you calculate the energy required for such a change of an A into B. The rest is left to the audience how to make a gold from iron or so. Yeah. And now you can calculate the energy for such a change. And in simple approximation, it looks very much the same as before. That's what we already had. That's the total energy, regardless of But now we have this term here, which is no longer constant. If we change the number of A atoms or the number of B atoms, huh? And this means that we get a delta E how did I write it here? I write it a bit different. I follow my manuscript, otherwise I get confused. So the dg from thermodynamics is, perhaps you remember, mu A minus mu B dNA. Here our dE, if you take this from above here, is Z over 2. What did I do here? Okay, I made 2 steps. So it's dNA epsilon NA, epsilon AA plus dNB epsilon BB plus and now, since we are in the semi-grand canonical, this is constant. So which one did I choose here? dNB equals minus dNA. And this omit this bracket here. And if you compare this with the expression above, you see that this is our delta mu. You just add a further energy term here, which resembles this asymmetry energy, but I think this is more by chance. So you just use this delta mu as a parameter. No? You give this parameter, and now you change the number of A atoms. If you want to make an B out of a, no, you make a B out of A. This means that the DNA is -1. Vice versa, it's a +1. So you add or subtract this term here to the total energy for either of these possibilities. Yeah. So in principle, it's very simple and very fast, and the concentration then adjusts according to the value you gave here. Besides, you have the standard type of expression here, counting the number of AB atoms. And of course, the number of AB atoms will also change if you transmute an A from B into A or vice versa. Yeah? So, and this is similar. Gu a couple of times spoke about the easing system or icing system. This is a model for a magnetic system, yeah, a ferromagnet. And there it's even more physical. You have your spins pointing either up or down, so the magnetization of these elementary magnets can be in either direction. You have certain interactions between the spins, which can lead to a unidirectional orientation or an antiparallel orientation. This depends on this parameter epsilon. But additionally, you can apply an external magnetic field. And this is just this term here. There we don't call it delta mu, but we call it H. That's the external field. If you apply an external field, you favor orientations of the spins in, say, this direction if the external field is in this direction, and then spins tend to become upwards. And if you invert your external field, the spins after a while will rotate in the other direction. So this way you can obtain a magnetization, that's the sum over all the spins, versus temperature curve, for example. Yeah? Which is 100% the same. Here we translate it into the language of binary alloys. Yeah? And I already showed this example here. Here, sorry, this is again in German because I took it from old manuscripts. Here you see for one case, this was supposed to mimic the nickel-aluminum system. In nickel-aluminum, the miscibility or the two-phase region is not at the center, so the jump is not at 50%, but there's the nickel-3 aluminum phase, which appears at 25% or around 25%. This is the one here, this upper phase here. You see it's starting at 22%, and then you get up to 25% or so. And here the alpha phase, the supersaturated nickel phase, here goes up to 10 or 12%, roughly 10%. And as I said, you have this strong hysteresis. This nickel-3 aluminum phase is an ordered phase, so it takes some time to nucleate. So probably, especially this branch of the hysteresis is a bit too far to the right, while disordering is typically much easier. Everybody knows it from experience than ordering. So probably the true phase boundary is more on the left side than on the right side here. Yeah. But the deviation is not huge. You see here it's 0.9 and here it's 0.85 or so. Yeah. And if you run it longer, you get even better statistics. I forgot to mention one point which is important for this nickel-aluminum system. Guru mentioned it yesterday very briefly, and perhaps I should explain it shortly here. What I typically do is to use interaction not only to the next neighbor, as I did it here all in these sketches. And there's a simple reason why we should use second neighbor interaction for this case of nickel-aluminum. It forms a gamma phase up to roughly 10 or 12%. Depends on temperature, of course. And then a gamma prime phase. And that's the basis of these superalloys, this gamma prime, yeah? At roughly 25%. This nickel-3 aluminum phase, it has this L12 structure, which I already mentioned. So if you like, it's the ordered FCC. Like this. If you consider only, is there a question? If you consider only nearest neighbor interaction, you get nice ordering, except, so it's only first neighbor. Into this L12 structure, if the composition is high enough, takes place. But what you obtain are antiphase boundaries with zero energy. I write it with uppercase because it's typically abbreviated as APB. And a special orientation of these APBs if they lie on 100 planes. So what's an antiphase boundary? Here it's arbitrary whether we put the nickel atoms on this side or on the corner sides, or we could, better, the aluminum, we could put it on the corner sides or on one of the face-centered sides. So we can have the same structure like this here. So I should perhaps cut it here, otherwise it's misleading. remove this part here. Like this. So this displacement by this vector here from here to here, since here you have a pure nickel layer, here you have a pure nickel layer, does not matter, does not change if you have only first neighbors. Yeah? Only if you take second neighbors here into account, these are the second neighbors, then it costs energy. And this, of course, generates very strange microstructures if you have zero energy antiphase boundaries. And by the way, this is also experimentally effect that 100 antiphase boundary have much lower energy. They don't have zero energy, but lower energy than 111 antiphase boundaries. And that's the origin of this yield strength anomaly in the superalloys. Yeah? So that the yield strength goes up with temperature. Because in dislocations, if you have these super dislocations, pairs of dislocations with an antiphase boundary in between, the first one creates the antiphase boundary, the second corrects it. And since the glide plane is 111, this antiphase boundary lies on 111 planes. But now if you raise the temperature, as I said, the 100 is cheaper energetically. Then they cross-slip, if these are screw dislocations, they cross-slip so that these antiphase boundaries move into a 100 direction or orientation. But this object is no more mobile. Yeah? So the first would migrate on another slip plane than the second one, so it creates an antiphase boundary here. This one cannot compensate this. Yeah? So this object is no more mobile. So this is why we have to choose second neighbor interactions. And that's what I did here in these simulations. This is with first and second neighbor interactions, and I tried to adjust the first and second neighbor interaction to more or less well reproduce the phase diagram. So you do this here, what I showed here, you raise the chemical potential, this is epsilon AA minus epsilon BB, step by step, and check which concentration it reaches. And after a while it will jump. And then you run it a bit further. And this you do for a couple of temperatures. I show it here for a set of temperatures from 600 to 1200. You see here the ending concentrations here. So you either read out by hand or write a small code to get these concentrations here. And this then generates this phase diagram. This is for nickel aluminum. So these are the points taken from this Monte Carlo here. Here you see the alpha, the gamma phase. Here you see the gamma prime phase. Here's the miscibility gap. These lines are just to guide the eye. These are not experimental data. It's different here for this case of copper cobalt, which does not show such a ordered phase, but it's very simple precipitating system, binary system. It's not really simple. It has a peritectic here and a strange liquid solid region here. But the interesting part is here the solubility line on this side and the solubility line on this side. And that's the experimental phase diagram, the dotted lines. So in this case, it more or less at least reproduces this side of the solubility line. This one is not that well met, but still reasonable, I would say. I used 2 different sets of parameters here, I forgot which one, to fit these pair exchange energies to this phase diagram. So that's the second thing I wanted to show before we continue here. This application of Monte Carlo for diffusion and for phase diagram calculations. I think we make a short break and then I continue with ATAT, or you want to continue with?
Do ATAT in the afternoon, I can do residence time, which will go with this.
Okay.
Then ATAT you can do, then I'll do cluster algorithm.
Okay, very good. Yeah, then I can take a small break.
Yeah, they can take a break by the time I set up things.
I should store everything. I think I forgot yesterday to upload my notes.
We'll do today. Okay, so this is a bit of a strange presentation because I am going to present work that is done by Ferdi, but if there are more detailed questions you can always ask him. So, here is the outline. So, we will start with a short introduction. Already Ferdi has done some part of it, what I had in mind about this L12 structure and so on. And then I will show you the alloy model that is the basis of the analysis. And this is an alloy model in which we have introduced a vacancy, which also you saw. That is why I thought that this lecture can be a continuation. And then you do the analysis for vacancy jump kinetics, which is what gives us the corresponding Monte Carlo algorithm, which is known as residence time Monte Carlo algorithm. And at the end I want to talk about a nearest neighbor bond model, just to know how these values are evaluated, and this paper is nice. I mean, it gives us an appendix how these values are evaluated, and then this GCMC for the construction of the phase diagram. So, everything is there in the paper, and the paper is from ACTA. It is written by Abhi, my thesis advisor, Haider was here, and Professor Martin, who was their postdoc advisor. So, this paper is from mid 90s, I think 98 or something. So, 97, 98, in that time it got published. So, I was a new master student at that time. So, this is using it's a kind of kinetic Monte Carlo because the time scales are comparable to real time scale, and so this is one of the KMC algorithms, and this is known as residence time Monte Carlo, and this is used for the study of precipitation of L12 ordered phase from disordered FCC using Monte Carlo, and this lecture is based on this paper. So, please do take a look at this paper. It is very nicely written, and then one of the papers that I read early to understand these algorithms and to understand atomistic methods. So, the alloy model that we have in mind is a rigid lattice. The sides are occupied by A or B, or they are not occupied, we say that it is occupied by a vacancy. Okay. So, that is a sort of terminology we use, and the atoms and vacancies interact through nearest neighbor bond energies, but the bonds themselves can extend up to the nth neighbor shell. Okay. So, you can say first nearest neighbor, second nearest neighbor, third nearest neighbor, and so on, but actual implementation is very simple. The AABB bonds extend only up to the first nearest neighbor, only AB bonds are extended up to the second nearest neighbor to avoid this scenario that Ferdi mentioned, that you have a 0 energy antiphase boundary. So, you do not want that. So, you correct for it. But the energy of the system in the most generic case I have written. So, the first one that is running the summation, the half is there because you want to account for the fact that the 2 atoms, you count the bond here and you count the bond back. So, it is half the bond. L is the site label. So, you have this lattice. So, you will go 1, 2, 3 etcetera. So, there are n sites, and n is the number of nearest neighbor shells. So, if you just have only the nearest neighbor, that will be just one summation, but if you go up to second nearest neighbor, which you do for AB bond energies, so it will go 1 to 2. Okay. Now, the third one is that in each nearest neighbor, for example, if you are in first nearest neighbor, if you assume that you are in a simple cubic, you will have 6 neighbors, right, or this is FCC, so you will have 12, and the second nearest neighbor will be 8. So, that summation m goes to k and l. So, the nearest neighbor shell for the nth site, how many of them are there for that nth shell, that is that summation. And then the last summation is basically site occupancy, sigma L is occupied by A or B or vacancy, and the neighbor shell that connects to, that is occupied by A or B or vacancy. That is what the sigma Lxi and sigma L plus m y I represent, okay. And Exyn is basically the bond energy. So, it is written in one single expression, but it is easy to see what it is doing. So, go to every site, you go up to some n nearest neighbors, you find out what type of atoms are sitting in these neighbors and multiply by their bond energy and calculate the total energy. So, this is the Hamiltonian that we are using for doing the computation, and so this is basically the internal energy, and entropy is anyway coming from the algorithm. So, that is how you get the behavior of the system. And in this model, they introduce only a single vacancy, which is not a bad approximation. If anything, probably it is more than what you would expect if you do on a lattice which has 100,000 atoms, then one would correspond to vacancy in 10 power minus 6 or something. That could be a good vacancy concentration to assume at relatively higher temperatures. So, lower temperatures is still lower, but where the kinetics is fast enough, maybe that is a good enough. And vacancy jump is needed for change of configuration. So, we introduce this terminology of configuration. So, what we mean by configuration is this. So, we have A and B atoms, right. You have introduced one vacancy. Now, this is one configuration, okay, and it is typically called the ith configuration, and then one of them is going to make a jump, and because there are z nearest neighbors to this vacancy, this from ith state it can go to one of the z states. What are those z states? Suppose if this makes a jump here, that configuration will be the one where these two are exchanged, or these two are exchanged, that is the second configuration. These two are exchanged, that is the third configuration. These two are exchanged, that is the fourth configuration. So, the system can go from this to any one of those 4 configurations only, because our mechanism is by vacancy jump mechanism, and because vacancy has only z nearest neighbors, it can only go from here to one of these z nearest neighbors, one of these z configurations. But the problem is, you can just do the regular Monte Carlo, like Ferdi said, that you will jump and you will jump back. Most of the times there is a correlation factor. Those of you who have seen Schumann, or there is another nice book called Manning for diffusion in crystals, you will see that this factor is known. In other words, statistically, the probability to have a neighbor as a vacancy is skewed once an atom jumps and the vacancy jumps next to it. So, now this atom has definitely more of a probability of seeing a vacancy, because it just made a exchange with the vacancy. So, it has certainty that there is a vacancy there. So, it tends to again go back, and it keeps doing this back and forth. So, I think sometimes this number can be what, 80% or something in FCC. Yeah. So, they are all wasted efforts. So, It keeps going back and forth before another jump happens, so that this is truly a movement of the atom or movement of the vacancy from that side. So, that means effectively this vacancy stays in that position for some time, and that is the residence time, and that is what we want to calculate, and that is how we want to match the simulation time with the real time, right. And the attempt of transition, that we assume that the vacancy makes this attempt with a frequency f. Okay. And this is the probability, and there is a little bit of there is also a figure in the paper to explain this. So, what is the probability of transition? And we are, like Ferdi explained yesterday, we are assuming that if the atom gets enough energy to go to the saddle point, then it will drop. So, the probability is only from ith state, how high is the saddle point to make the transition to the jth state, that is the nearest neighbor, that is the probability. And because there is a relationship between these energies and the saddle point energies, you can also write it is the same expression, but that saddle point energy J minus EI can also be written as EIJ plus E saddle point, right. Do you see that? Right. Here is the saddle point, and here is the I, here is the J. So, you can write the probability, and that is the expression that we are going to use, and we are going to assume that this ES is a constant, and it is independent of jumping species, it is independent of temperature, composition, local atomic configuration, etc. And this can be estimated from vacancy migration energy and self diffusivity in pure metals. So, okay, so and Ferdi also showed the way of matching the diffusivity by tweaking the energy parameters and getting the frequency of jump attempts by the jth atom to the vacant site. So, let us say that I have another atom J, and that makes an attempt to reach the vacancy, and what is the probability that it will do in the time interval delta t is nothing but the frequency of attempt times the time interval, and that is given, the frequency is f, and this is the probability times delta t. So, that gives you the expression to calculate the frequency of jump attempts in a given time interval, how many attempts will be made. Now, time enters the formulation through this factor f, right, that is the attempt frequency, that is what is setting up the time scale. If it is making many attempts for the same fraction of attempts being successful, you will see faster diffusion. If it is making lesser number of attempts, you will see slower diffusion. And this is where it connects to the paper of Gillespie, which also Ferdi referred to, and this is a standard reference, you will see, it is an important paper, but this is for reactions. Okay. So, this analysis, the mathematical analysis of the vacancy jump kinetics is based on this paper, and some of the results that I am putting there is from the paper. You can go take a look at it. Probably it is a good idea after doing this course to go read some of these papers. So, what is it that we are looking at? Let us say that the system arrives at configuration I at some time t. Okay. It is going to stay in this time in this state for some amount of time, okay, and then it is going to make a transition, and it is going to make a transition to one of the states that is available. Okay. What we want to know is that the joint probability, and that is called PJT, that the system makes no transition in the time interval. It arrived at t, and then it is going to wait in this state for some time Ti, and then within the next delta t it makes the transition. right. It arrives here, waits here for some time Ti, that is first it has to wait. Then the next one it is and it has to make a jump to state j in time interval dt. That is the joint that is why it is Pjt. Okay. What is it? What is the probability? That joint probability is what we are interested in. So, the system makes no transition in the time interval Ti to Ti plus T, and that the next one that it makes is to state j, and that it has to make within the time interval which is only increased by dt. So, if P0 t is the probability at time t that no vacancy jump occurs in the interval, okay, and that is, this is where they refer to Gillespie's paper, that it is exponential minus t summation k 1 to z gamma k. Okay. So, if you want to get Pjt, you can see P0 of t gamma j dt will basically give you the probability which is the joint probability, because these two events and in the probability. Okay. Now, the vacancy kinetics, what does the vacancy kinetics depend on? It depends on how much time is spent in I, as well as what is the position to which, or what is the configuration it takes after the time tau in the small interval dt when it makes the jump. So, we need to know two things to get the kinetics. First, how much time it waits here, and which is the position to which it jumps, and they are determined probabilistically. That is what the simulation is basically doing. It is calculating at every state how much time it is spending, and after that it is also deciding which is the jump it is going to make. So, the probability that the system is in state I before making the transition is given by that P1t, and P1t is some j1 to z Pjt, and so if you write this nu as a summation j1 to z gamma j, you can write P1t as nu exponential minus nu t. Okay. So, now this amount of time is spent, and that is irrespective of which jump it is going to make. Okay. It is going to wait here, and after that it is going to make one particular jump. Okay. To calculate the time that it is going to wait, which is known as the residence time, you can choose a tau which is minus logarithm of R1 by nu, where R1 is the random number that you generate between 0 and 1. Why? If you choose this, the residence time will obey that probability distribution P1t, and you can see why, right. Tau, right, go back and you see here what is P1t, right. If you put this tau here, you will see that it obeys this probability distribution, right. Then nu will go away, and you will have logarithm exponential will go away, and you will just get the same probability distribution for the system. So, we have chosen residence time which obeys this probability distribution, which we know is the probability distribution for the system to spend time tau in this state. Okay. So, that is the first random number that you have to do. Of course, the second random number you have to do, and that is the next transition occurs to the state j in time after this tau. So, that is a conditional probability. P2, that is j given tau, that is the system waited at I for tau time, after that it is making the transition j. So, that is the conditional probability, and by definition that is Pj of t by P1 of tau. And so, you choose a second random number, and again in the paper there is a nice picture saying that okay, there is this different probabilities or frequencies for jumps tau 1, tau 2, tau 3 etc. Then you take a random number and you find out where it falls, and you pick that state to be the next state to which this makes the transition. Okay. So, there are these two random numbers, and using these two you move your algorithm, you make your Monte Carlo steps. Okay.
Maybe you just sketch this.
Yeah. So,
I found it always very
yeah. So it had this.
I think it's also from
It's from Gillespie, is it? So basically all the jumps it can make you put, and then you take this new gamma, suppose it falls here, that is what you are going to choose, right. Where does it fall? Depending on that state you are going to choose. Okay. The figure is much better in the paper if I can locate it.
One probability which is far higher than the others, then if you choose a random number in this interval, it's very high probability that you hit just this interval and not another one. So that's perhaps
Yeah.
intuitive.
Both the figures were. Show the other one. Yeah, here is the one where they are showing why the saddle point is the energy expression that we wrote, including the saddle point, that is the schematic, and this is the one where you make this, right. So, you fall, which state you are falling in, you make that transition to K. Okay. So, this is the second random number that you need. So, with these two random numbers you can get to an algorithm which now accounts for two things. Sorry. I do not know why, but whenever this is connected to any other device, even my Wacom tablet, I find that this mouse behaves a little bit odd with connected to other devices. Yeah, the schematic probability array I wanted to sketch, and I showed you from the paper. So, that is what so there is a set of probabilities, you take a random number, and then the easiest way I found to imagine these things is that, let us say that for some reason the probability of making this jump is smaller than the other three, which means if you arrange them, it is very small probability if you choose a uniform random number that you will end up in that interval, because overall that is small, right. You will end up in whatever is more probable. So, it is basically the same thing with all these random numbers that we are doing. So, this is known as residence time Monte Carlo. You have to choose the right transition, and you have to wait the right amount of time before making the transition. So, there are two random numbers that you need to generate. One, which is on the second line, helps you choose the right transition. The one above, that is the first random number that you choose, tells you how much time you have to wait in the current state before making that transition. So, that is how it makes a more realistic Monte Carlo algorithm. Okay. Now, here before, this is pretty much it what I wanted to show. You can take the code that I have given and modify the code to do this, and in fact, the same code you can also modify to do the GCMC also, that they are all, we had Glauber, we had Kawasaki, you flipped or you changed, but you can change the energy term a little bit and then change the like Glauber you do, then you will get GCMC, and you introduce more random numbers and do this, you will get. But before you go and do the change to the code, this paper also has a nice appendix, because this is also some of you have been asking for. How do I choose values? How do I know that the parameters I have chosen are nickel or aluminum or whatever? So, for that there is a very simple model. These are known as bond breaking models, and some of you might have already seen these kind of models. For example, in Porter and Easterling, surface energy is described using such a model. in the third chapter first you look at. So, a random direction you take and you take a crystal and cleave along that random direction, and you basically count the number of broken bonds and attribute that as the surface energy, right. So, these kind of broken bond models are common, and here we are using one such broken bond model to identify the parameters associated with the system. So, in that paper those parameters are also given, and this calculation is given as an appendix. How do I calculate these parameters? So, you consider a pure metal with only nearest neighbors, okay, and a vacancy, one vacancy, because that is the scenario we are dealing with, right. So, because I am going to consider only the first nearest neighbor, I am going to avoid using the superscript 1, but in the paper it is written n, okay. So, but n is 1. So, now consider what is the cohesive energy of a pure material. It is the energy required for you to break all the bonds, and if that material has z nearest neighbors, so z by 2 times EAA is basically the cohesive energy. So, if you know cohesive energy for nickel or aluminum, you can evaluate epsilon AA EAA for nickel, right, or EBB. To evaluate this quantity EAA and EBB, all you need is the cohesive energy. So, it is a very simple minded model which assumes that there are only nearest neighbor bonds, which is strictly not true. I mean, you also know, but this is a good model, and you see that there is in the paper there are also results later to show that they are able to capture some of what is happening with the gamma prime precipitation from disordered FCC in this system. Now, if you know the vacancy formation energy, you can also evaluate the vacancy A atom interaction energy. The assumption that is made is that vacancy energy is considered to be, interaction energy is considered to be 0, which makes sense because you can consider just empty space as consisting of all vacancies. Like I said, I mean, there is nothing like a vacancy. There is a site which is not occupied, which we think is as vacancy, so it can be considered. But there is a trick here. If you just consider the vacancy formation energy to be the energy that is required for breaking all the bonds, you get more than what you would actually see in a real system. That is because you break the bonds, take one atom, and that atom does not disappear from the system. It goes and sits on the surface where it can recover at least 50% of the bonds. Okay. So, a good estimate for vacancy formation energy is by taking a bulk atom and placing it on the surface. So, you have to break Z by 2 bonds, but you will recover half of them. Okay. So, that is how we calculate the vacancy atom interaction energy. So, now you have EAA, EBB, EAV, EBV, EVV is 0, all of them up to first nearest neighbors. EAB also has to be calculated, and in the case of EAB, we have to go at least up to second nearest neighbor to get the L12 properly. Okay. How do you get EAB? And first neighbors are unlike neighbors are preferred, second is like neighbors are preferred. So, there is a change in the sign, and that value is chosen using a grand canonical Monte Carlo to get the phase diagram match with the systems that they had in mind. I take different compositions, it should correspond to different supersaturations. So, I construct a phase diagram by choosing EAB and choosing it to be consistent with the L12 formation, and that is how the AB bond energies are evaluated. So, this is one part, how do you get the bond energies. Now, these bond energies are in which units? What is the unit of cohesive energy? What is the order typically? So, What is the order of bond energy? Forget cohesive energy. Cohesive energy is Z by 2 just multiplying bond energy. So, what is the order of bond energy? Electron volts, right. So, you will have these energies in electron volts, but you remember in all your algorithms the right. So, typically you will also normalize it by delta E by K or KBT, which is the energy. Okay. That is why temperature is given, I mean Ferdi was also giving, temperature was given as what, 1, 0.1, 2 and so on. Okay. So, that is because we know that these are energies and they have some units, and natural unit to normalize them is KBT. So, we take temperature to be normalized, and these values also will then be, you will see in the paper that they are given as some 0.025, 0.2, 0.3 numbers like this. Okay. So, that is how you make the mapping from what values you are using to what system it is. Okay. Like Ferdi showed, okay, you can also map to kinetic properties like okay, diffusivity by also fixing some of these energy parameters. So, you can also, so how many parameters you match, to that extent it is closer to the real system. But you have to remember that these are all approximations, assuming that only bond nearest neighbor bonds is an approximation, only assuming pairwise interactions in a metallic system is also an approximation, right. In LJ you saw that you have to use EAM potential or something in molecular dynamics. LJ is not what you use EAM for metals. So, but to the extent that these capture, they do get many of the physics that you want to model correctly, and that is how they are used. So, that is what you should also look up if suppose you want to use a specific system, then you look up for energies like cohesive energy, vacancy formation energy and so on to calculate these parameters, which you will put into the model then, and that will mimic the system that you are looking at.
So, in this expression this delta is a cohesive energy, not a bond energy. So, whatever
this delta E, no, this delta E is the difference between the two configurations, EI, that is what this delta is. But this EF and EI are functions of the number of A atoms, number of B atoms, and the epsilon AA, epsilon BB, epsilon AB, and in this case also epsilon AV, epsilon BV and so on, right, because we count the number of bonds, we calculate their energies, and then we flip, we count the number of bonds and their energies. So, these EI and EF are all functions of this. This is what we calculated from the cohesive energy, right. So, this energy will be the same order as those energies.
because the sparks, what the issue we face that there we have to put the delta E by KBT to the ratio 0.01, 0.02. So, suppose you want to do this Monte Carlo at some particular temperature, so at that time we don't know how to choose this E value.
No, E value is given depending on your system's cohesive energy and so on, right. The GCMC simulation he showed for NiAl, if it is Ni, Al, at least we assume that with the temperature those are not changing. We are assuming the same numbers for them, and then the temperature which appears here is how the phase diagram is changing, right. So, we are sort of assuming that the bonds are not really changing with cohesive energy. Probably is that there is also sometimes, I mean it is called sublimation, because you are not supposed to take the bonds are broken, but it has gone into a liquid state. That is not the right thing. You are just taking the solid and then breaking all bonds and taking them apart. So, So, it sublimates. So, that is the energy that you should use. If there is energy of sublimation, then that is what you should use to estimate. So, that is the key word, we are just estimating these parameters, assuming that just nearest neighbors, just pair interactions, can I capture the energetics associated with this system, and generally it will scale high melting, then you will get larger energies because cohesive energy is high, low melting. So, correspondingly thermal effects will be captured in your model because you have now gotten energies which scale according to these. Okay. So, that is how you think about it. Okay. Any questions? Ferdy, any comments?
Perhaps a short comment. I mean, this residence algorithm in principle could be applicable to any kind of Monte Carlo procedures, but it's in particular suited to study vacancy diffusion. Because if you think, I mean, what you basically have to do in this residence time algorithm is that you consider all the possible transitions from one configuration to the next, as I call it, yeah? So jumps of the vacancy in our case. Yeah? So here in this square lattice you have 4 possibilities, on an SCC lattice you will have 12 possibilities. For these 12 possibilities you calculate for each of these the respective probability. This is, I think it was Pj or so. Yeah? Now if you can think of AB exchanges somewhere in the lattice, you don't have 12 possibilities, but if you have 1 million atoms, you have 12 million of possible changes. If you have 12 neighbors. And then you have to take these 12 million of possible changes, which of course is much more time consuming as just consuming 12 probabilities than 12 probabilities. Yeah? That's why it's preferential to use it in this vacancy diffusion thing. A long time ago I wanted to, for whatever reason, I wanted to know what happens on arbitrary pair exchanges. Yeah? So I tried to write a code which is possible to take all these so a million of exchanges into account, and with proper bookkeeping. I mean, if you have this exchange in one position, it does not change the probabilities in other corner of the system, so you can keep all these, but it requires a huge amount of bookkeeping. That's what I remember from this time. Yeah. Unfortunately, the kinetics we are interested in is controlled by vacancies, and this very low number of possible exchanges.
So, if you look up for kinetic Monte Carlo, there are lots of resources. There is a chapter by Woter in some radiation damage book, which is a good introduction also, and Bataille is another name I found. There is a paper which reviews kinetic Monte Carlo, and at the end he has given a code, but unfortunately it is given as an image format. So, you have to type it in if you want. But this resource is another one which Ferdy did show on the very first day. There is this person called Kai Nordlund. Okay, this is the name. And his homepage, even in those days when I was trying to do this in early 2000s, had lots of information on atomistic simulations. And one of them is the lecture on kinetic Monte Carlo, and he refers to some nice papers also, this Leibowitz paper here, and he explains what this is, and somewhere he says kinetic Monte Carlo and residence time, he really does not make the distinction. Somewhere he says these are these days called residence time, and that is what we will call this process. And he gives all these algorithms and nicely explained. So, I found, so here is the algorithm. for you if you want to write a code or want to write some script. His web page also had lots of scripts, and it was also a page where you could download these Fortran routines from Allen and Tildesley's textbook, which had this appendix of some 16-17 codes, linked lists and Verlet algorithm and things like that. So, all of that you could download from his site at that point. I do not know if they still have it. So, you can see where the random numbers are, how the time is updated. So, the algorithm is given, and you have an implementation of this in C anyway from Ferdy's code. So, you can also take a look at that code. So, but at some point if you that was not residence time? Ah, okay.
But I can upload this 3D code, so too bad.
Yeah. So, this is where he says this algorithm is known as residence time algorithm or n-fold way or BKL algorithm or the kinetic Monte Carlo algorithm. So, residence time and kinetic Monte Carlo he does not distinguish, and he says I would recommend using residence time since it is nowadays quite common use, but this itself is quite a while ago. But nowadays you also see kinetic Monte Carlo. Sparks, for example, talks about only kinetic Monte Carlo and rejection kinetic Monte Carlo, something like that. So, okay, so this is a nice resource.
One further remark, can you scroll up a bit, because there is a second random number, one page above.
1 by r without the random number, same long time average in the. This is what you wanted to make, yeah.
I mean, in principle, what you do, what Guru explains, that you choose two random numbers, one to determine the time step, and the other one to determine the proper exchange which is performed. And this, more or less, this first one is not strictly necessary. It just means that you calculate the length of this time step by introducing some randomness again, so it fluctuates. In average, this time step is 1 over the total probability. So you have, I don't know, here you have four possibilities. So you sum up all these 4 possibilities, so the probabilities of these 4 changes, yeah. Take the inverse, and then you have the average time step. The mistake you make is, as far as I remember, very small. So in principle you can save the time for the second random number, which costs quite some time. If you make million steps, you can save this time and do a few more steps instead. Because this is log u over r, what is it?
Yeah, log u by r, what we called as log r1, that is by r. And this new he calls as r.
Use the second random number.
Yeah.
Just used choice of the.
So these resources are really nice because he also gives this kind of practical these things which are hard to come by. At that point, Rappaport was later, right? We had only Allen and Tildesley. I don't remember seeing even Frankel and Schmidt at that time. So Nordlund's website had all these kind of tricks and tips for us. So, and it is still a good resource. I think the page is still open. And many a times you might have ended up on his page by looking up some Monte Carlo molecular dynamics. But
They also have their own
Malden, yeah.
their own MD code package.
Okay, so that is all I wanted to say about residence time. Please do try to implement and get back to us if there is any problem. The afternoon we will talk about one algorithm which is to analyze the clusters. So, you saw lots of simulations, there were lots of particles coming up, how many are there, what is their size, what is the distribution and so on, can be obtained using an algorithm which is called Horschen-Koppelmann, which is what we will discuss in the afternoon, and Ferdy will talk about ATAT and cluster variation in the afternoon.
Do you have an idea, in the Ovito, there's also a cluster recognition algorithm implemented. Do you know which algorithms they use?
I am assuming all of them will be Horschen-Koppelmann, because I think that is the best for.
No,
if you have a pure material. See the Hauschen-Koppelman, you will see in the algorithm. So, you have to identify the atom which makes the cluster. So, if you have a pure material, it will say that entire thing is one cluster, which is true. Only if you have a binary system and you have some B atom sitting, then you can go look at B atom clusters. In fact, even there if you look at A atom clusters like what Ferdi had, blue in which some orange atoms were forming the precipitates, if you look at blue it will still say only one cluster for the blue, because that is single cluster, and I will show the algorithm in the afternoon. So, you will see why it is one cluster. Only for the precipitates then it will start labeling them as different. But I am assuming that it is Hauschen-Koppelman, because all of them are just finally union and find. It is only the way you do the.
I remember that I had certain problems when we did this nickel aluminum things. There is a precipitates, they have this order structure. So you have one B atom and the next B atom is only on second neighbor shell, then all the first neighbors are A atoms.
So, it will not label it as a cluster?
Yeah, I mean you have to do it
up to second neighbors.
But then there is also a lot of random connections.
Ha.
So I try to modify it that I count it only if there are more than one, say 2 or 3 or so
I see.
neighbors. So
But if you map this L12 to a cubic structure with a motif, it will work, is it?
no, I think it's the same. I think there is a connectivity. I mean, on an
Because then you will look at if you have a motif and then you will only look at.
lattice you have just 6 nearest neighbors.
Right.
So the condition or the probability that you have just a random neighbor is pretty high.
I see. So it will also show lots of.
I think you have kind of calculation problems and so on.
I see.
I roughly remember that I played it.
Okay.
This
Yeah, I didn't think about that at all.
I was wondering whether it makes a difference, because I mean, if you think of having such connections between precipitates, then it would be much easier for Poissoning, for example,
To make the jumps.
such a chain. So sometimes I try to figure out whether this makes an influence or not.
I see. Yeah.
Okay.
Anything else? Okay. So today also they have some recording here. So what we will do is we get back here by 3:45, okay, and start at 3:45. So we end at 5:45. Okay.